Good morning. I'm Dr. Boukhalkhal Hicham from University of Science and Technology Hawari Boumediene of Algeria. Allow me to dedicate this work to my father, who left us in the last June. This presentation deals numerical modeling of CFST column to I-beam and plate joints. To present the work, we will follow the following plan. We start with an introduction. In multi-story steel structures, the application of tubular profile with or without infill concrete is interesting because of their advantageous properties, such as strength to weight ratio and their efficiency as a completion element. The current study aims at developing a 3D numerical model to access the mechanical behavior of I-beam to CFST column joints with end plate. The moment rotation curves predicted by the finite element models have been compared to experimental tests. Due to their symmetrical shape, hollow section joints are particularly advantageous, being more resistant to axial forces. In practice, there are different ways to connect open section to hollow section column, such as flow drill, hollow bolts, and welded studs. As well as the connection ability will be almost controlled by the deformation or strength of the face of the hollow profile and not by that of individual bolts. Several studies on the performance of I-beam to hollow section column connections with and without concrete using different types of fastening technique have been developed. The main conclusions are as follow. Different fastening systems and techniques currently available. The loaded face of hollow section column can be reinforced with a backing plate or more effectively by increasing their thickness. The conclusions drawn clearly show that it's necessary to improve the stiffness of the loaded face of hollow section column by using the filling concrete. An experimental study on specimens subjected to monotonic loading was developed in the Coimbra University. They were carried out on test specimens subjected to monotonic loading comprising 3 different configurations. This figure illustrates the configuration of the test with the loading frame and the test pieces, as well as a general view with the boundary conditions. Pause now to present numerical models proposed in this study. Based on the experimental result developed in Coimbra, 3D nonlinear finite element models have been developed to analyze the mechanical response of this type of connections. The configurations are organized as follows. In this study, the main steps of modeling connection with ANSYS software as described in the following chart. A solid 186 element was chosen to represent the concrete infill, IP beam, the end plate, and the square hollow section. And the element solid 187 was chosen to represent welded stud. The material and geometric characteristics adopted for the numerical models are the same with those used in the experimental work. The tetrahedron type mesh has been adopted for for all connection components. In order to evaluate the behavior of I-beam to column CFST under monotonic load, static analysis is carried out by the application of a moment at the end of the beam. The boundary conditions are assumed to be fixed in both ends of square hollow section. The nonlinear analysis was adopted in this study. Finally, extract the results. To validate our results, the finite element models are compared to the experimental results merely in the form of momo-rotation curves. From the previous figure, we notice that the experimental curves of momo-rotation are located almost the bound of 10% by comparing with the curves of the numerical models. The same remarks for the other configurations. The experimental momo-rotation curves are almost in the 10% range compared to the numerical models curves with minimal margin of error, and consequently the developed numerical models proved to be suitable for use. This figure shows the distribution of the horizontal stresses at the column face of the EN16 and the EN17 models for each level of applied moment. The numerical model EN16 stress distribution shows that at the level of the second row of studs, the column space attained the plastic phase for a moment equal to 25 kN/meter. For the first row, this moment is 32 kN/meter. In addition, it can be noted that the major parts of the column's loaded phase have yielded before the load reaches 14 kN/meters. For EN17, it could be observed that the phase of the CFST column yields for a moment equal to 22 kN/meters. Consequently, the joint of configuration B presents a higher resistance for EN16 and EN17. In terms of stress concentration and yield zones, the figure depicts the difference between the two configurations. The study of the state of deformation allows the determination of the failure point of the studied element. The comparison between the two numerical models EN13 and EN14 shows that the face of the CFST column will be damaged at moment equal to 42 kN/meters, with a decrease of 21%. This was due to the fact that the precision and symmetry of the stud rows, as well as the loading direction, play a significant role in the behavior of the joint, thus directly influencing the joint failure load. The numerical model EN16, the moment corresponding to failure of the interaction zone is equal to 57 kN/meters, while the EN17 is 40 kN/meters. In the last figure shows the deformation envelope in the CFST column face for the two models EN19 and EN21. The column face of the numerical model EN19 attains the failure phase when the moment reaches a value of 50 kN/meters. On the other hand, failure in the EN21 model occurs by the stud failure due to its considerable thickness. The end plate remains within the elasticity range for positive moment tests such as EN13, 16, 19, and 21. For the negative moment, it could be noted that the plate yields at the extended part, which is a direct consequence of the high level of the moment reached due to the membrane action at the column face. In addition, for all the numerical models studied, the flanges of the beam did not attain the plastic phase. We observed a detailed study of the behavior of each joint compound and their monotonic loading was carried out. The numerical results obtained out the following conclusion to be drawn. The main compound in the models studied was the column-loaded phase, which is the first element that attained the plastic phase. If the premature failure of the start could be ignored, this compound would be the most relevant joint compound. The column phase stress distribution was essentially unidirectional in the horizontal direction, while the observed variation of the stress intensity along the height of the face justifies by the hypothesis of an elastic force distribution between the multiple columns rows. The influence of the low direction over the maximum strength and the initial stiffness was not evident, while the end plate type had a significant influence in the behavior. In comparison to the joint with a flash end plate, the extended end plate joints could significantly improve the bearing capacity and the initial rigidity of the joint. Thank you for watching.